All right. Hello, pre-calculus students. This is a continuation of the work that we did yesterday, and we're going to use long division to find imaginary roots. Well, first thing I want to look at is let's take a look at what we know. It's a degree 4 polynomial, so there should be 4 roots or 4 solutions, but they could be real or imaginary. And if I look at the graph of this function, I can identify that we have 2 solutions right away, and those are 2 real solutions. So looking at my graph, I can see x equals -6 as a solution, and I can see x equals 1 as a solution. But if we know the solutions, if I move the 6 over with addition, then I have the factors. So if I subtract 1, bring it with the x, now I have the factors. So what that means is I could take x plus 6 and divide it into this polynomial evenly and get a really nice answer. And then I could do the same thing and plug in x minus, or divide x minus 1 into this polynomial, and I would get a remainder of 0 as well. But if I'm going to do both of those, why don't we FOIL this out right away? If I expand, I end up with, oops, I did it in a little different order. I'm just FOILing this out, and then if I combine my terms, I end up with a trinomial that is equivalent to those two factors being multiplied together. So why not just take f of x and divide it by x squared plus 5x minus 6? And that's our goal, is we're going to use long division to help us basically get rid of the two factors that we already know. So just what we did yesterday, we're going to go ahead and do long division. I want to take this x squared and make it look like the starting x to the fourth. So what do I have to multiply x squared by to make it look exactly like this? I got to multiply it by another x squared. That'll give me x to the fourth. And then everything else has to be multiplied by that same x squared. And then when we do that, we always subtract. But I don't like to think of it as subtraction. I like to think of it as adding the opposite value of each term. So notice how each piece changed. So then when I do this, if I do it right, the x to the fourth will go away. And then we're left with a 6x to the third and a 40x squared. Now technically, we didn't do anything with the other two terms, so that drops down. And now it's like a brand new problem. Let's now take this x squared and make it look like 6x to the third. Well, how do I do that? I need to multiply it by a 6x. And we're going to, if you want, you can draw your arrows to all of the pieces, but they're all being multiplied by a 6x. All right, and then we're going to subtract the entire trinomial, which again, we like to think of it as adding the opposite. When I do that, first two terms add up to 0. The x squared terms gives me a positive 10x squared. And then I end up with a plus 50x. And then we didn't do anything with the minus 60. So that's just going to drop down. And now it's basically like that same problem again. We're going to go ahead and how do I make the x squared look like 10x squared? I multiply it by 10. Multiply all pieces by 10. So, and you should notice something, hopefully. We're going to subtract, which is really adding the opposite of each piece. And notice the x squareds go away. 50x minus 50x goes away. Negative 60 and 60 goes away. I'm left with a remainder of 0, which means that this trinomial divided perfectly into it, which is why I have two real solutions. But now we have to look at what's left over, because what's left over is an x squared, and this answer, this piece that's left over, has two answers itself. So I have to solve that using whatever methods I know how. So I'm going to scroll down. Now I have to find the zeros of this function. There's a problem, though. There's no factors of positive 10 that add up to give me 6. If there were, then those would be real answers and they would be present on the graph, which means this is going to have an imaginary solution. So how do we do that? Since I know it can't be factored, I'm going to take the coefficients of the trinomial A, B, C, and we're going to apply the quadratic formula. So you can sing your song. X is equal to opposite B plus or minus the square root B squared minus 4AC all over 2A. All right. So hopefully you are well versed in this. I'm going to go through it pretty quick. I always like to fill in my blanks with the numbers. So what is B? Well, B is 6. So opposite of 6 is negative 6. Plus or minus square root of B squared, that's 6 squared, minus 4A times C all over 2A. And we're just going to simplify. We get negative 6. And I know that this piece right here is 36. And then 4 times 10, so this is really 36 minus 40, which is negative 4. That's called the discriminant, if you remember that. And that tells us if our answers are real or imaginary. Since it's a negative square root, we know for sure we're going to get imaginary numbers. All right, so now I'm going to basically take the square root of negative 4. Now this is side work. If those of you that were in geometry or algebra 2, we always kind of went like this. You can split this up as the square root of negative 1 times the square root of 4. The square root of 4 is 2. The square root of negative 1, that's the imaginary number I. So the answer to the square root of negative 4 is 2I. And the plus or minus are because we're taking the square root. So then I just have to actually set up my two answers. All right, we're going to use 1 with the plus and 1 with the minus. Now, we can't actually add negative 6 plus 2I over 2. However, see this divide by 2? Each item is divisible by 2, so 6 divided by 2 is 3, and 2 divided by 2 is 1. So here's my first solution, and you may know that its conjugate has to be a solution as well, so I should get the conjugate of this answer when I simplify using the subtraction one. That's the idea of conjugates. But let's just double check. What happens when I do 6 minus 2I? Well, 6 divided by 6 is negative 3. Sorry, negative 6 divided by 2 is negative 3. Negative 2 divided by 2 is negative 1, and then the I stays. So I'm just going to write the word conjugate next to it, because when you guys get to calculus, it's pretty important that you understand that. All right, there's the first example. So now we know all four solutions. Right? We've got two imaginary, and from the graph, we have two real. A total of four solutions. All right, last one. Let's take a look. Now notice four solutions. They are all real. However, look at one of them is kind of that weird irrational number that I believe this is even rounded. So let's use that same idea and go ahead and try this. What I'd like you to do is hit pause and try this problem on your own. And then when you're ready, hit play and we can go through it, or you can double check your answers. So what do I know? All right, I've got an answer. Right now, I have an answer of x minus 3, right? That's a guaranteed answer. And this one's not friendly. This one's friendly, though. X minus 1. So I've got two answers. But where are their factors? We're going to move the 3 over. So x plus 3 is a factor. Move the 1 over. X minus 1 is a factor. So here are my roots. Here are my factors. And I could divide each one individually into this trinomial. Or what if I just multiply these? If I expand them out, I get x times x times negative 1, 3 times x, and 3 times negative 1. And if I add them together, I get a new trinomial that will divide perfectly into this with a remainder of 0 because these are solutions. So I'm going to take that trinomial and I'm going to divide it in. Notice 4, 3, 2, 1. There's no missing terms, so I don't have to add any spacers or place values. And then I'm going to do this real quick. We're going to multiply the first term by x squared, so it looks like an x to the fourth. I'm going to multiply all terms by x squared. X squared times 2x is 2x to the third. X squared times minus 3 is minus 3x squared. And then I'm going to subtract the two trinomials, but I like to think of this as adding the opposite. So the fourths go away. Ooh, conveniently, so do the 2x to the thirds. And then what's left over is a negative 3x squared minus 6x plus 9. So we didn't use those, and they drop down. Well, now we're going to treat this as if it's a brand new problem. I'm going to multiply the x squared by negative 3. So it looks like this one. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 2 is negative 6. And negative 3 times negative 3 is positive 9. Now notice, those are identical, which is hopefully proof that why we subtract them, they need to reduce out, or we add the opposites. That becomes addition, addition, subtraction, and add, 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 remainder of 0, which means x squared minus 3 is left over, right? So if that's what's left over, this piece will have two, look at x squared, it'll have two solutions. And our goal is to solve them and figure out, are they real solutions or are they imaginary? Well, we already know they're real because you can see where they cross. So now I'm going to take whatever was left over from dividing out this trinomial. This is what's left over of f of x, and we're going to find its 0. Now notice, you don't need to do quadratic formula because you have one variable. You can just use algebra, add 3, and then take the square root of both sides. When I do take the square root of both sides, you have to remember you get two answers. Right? So I end up with a plus and minus square root 3. Notice there are two answers here. Well, one of them is the negative square root 3, which is right here, negative 1.732. And the other one is a positive square root 3, which is right here. So there you go. We now have all four solutions. We've got the plus and the minus square root 3, and then we have the original x minus 3 and x plus 1. All right, that's all I got. Hopefully this helps.